Here we're looking at a situation where a hand is pushing two boxes that are moving together to the right across a frictionless table. The blocks are accelerating together at 9 meters per second squared. So that's an acceleration constraint that they have to move together. We want to draw an interaction diagram and a free body diagram for these two boxes, and then find the magnitudes of each force. So when we look at a interaction diagram, we're looking at what is actually in this situation. We have a hand that's pushing on one block. That block is pushing into another block. These blocks are sitting on a horizontal table. So we want to show the hand is pushing on block A, and so we'll put a connector there to show that they're pushing on each other. A is then being pushed into B, and so we'll have another connector showing that interaction between A and B. A and B are both sitting on a surface, and so there will be a normal force of both of them sitting on the surface. Even though it's frictionless, there won't be a frictional force. All of this is taking place on Earth. And so we'll also have a force of gravity of both blocks acting on Earth. So we have mg, we have our normal forces, and we have the hand pushing block A, we have A pushing into block B. Now what we want to be careful of, what we can say is the hand would have to be connected to an arm, which would be connected to a shoulder and a body and feet. That feet are then connected to the floor, etc. We could let this get as complicated as we want to be, but we're going to assume that the person connected to that hand is not moving, and that A and B are what we're interested in. And in that case, A and B are our system here. Now, when we want to draw free body diagrams for each, we draw a circle representing A. We know that A is going to feel gravity downwards, and A will feel a normal force upwards, and we know here from experience that the normal force should be equal and opposite the gravitational force. It's moving flat across the table. There's no vertical acceleration, so the normal force and gravity should just cancel each other out. We also know that there's a force that the hand is applying on A, so we'll write that as the force of the hand acting on A. So basically we have these two forces, or our vertical forces. We have this force that's pushing A to the right, and this force here, if A is pushing on B, B has to be pushing back on A, and so there has to be a force acting back to the left. That is the force of the reaction of B pushing back on A. You'll note here as well, we made it so that there's a net force and thus a net acceleration to the right, because these blocks together are moving to the right. So that has to be the case. When we look at B, there's only three forces acting on B. There's the force from A, and then the normal force and gravitational force. So again, when we're making a free body diagram for B, we draw a dot that represents B. There is a force of gravity of B. We'll make it larger than A, because B is larger than A, and so it would feel a greater gravitational force. But it's still staying on the table, and so it would have a greater normal force as well. that would balance out the gravity that it would feel. The only other force here on B is the force that it feels from A. And if A is trying to move to the right, then B will feel like it's being pushed to the right by A. This is the force that A is exerting on B. And we'll notice here that these two these two force vectors are equal in length and opposite in direction because they are an action-reaction pair, and so they're equal in opposite direction. They show up in the two free body diagrams. When we try to finish our calculations, what we're going to do here as part of one of our simplifying assumptions, we'll assume that gravity and normal force balance out, so that these blocks are sliding across the surface. That's what we're told, that they are sliding across a frictionless table, so we'll assume that there's no vertical acceleration and that they're just staying on the table. In that case, we'll have a Newton's second law. Sum of the forces is mass times acceleration. We'll have that for block A and another one for block B. And we'll remember, if they're accelerating together, as we're told, then we know that the acceleration of A will equal the acceleration of B in our Newton's second law equations. So in the first instance, the sum of the forces acting on A are the force of the hand, which is to the right. So that is a positive force. We also have the force of B pushing back on A, that's to the left, and so that is a negative force. And all of that equals the mass of A times the acceleration of A, but since A and B have the same acceleration, we'll just leave the acceleration as a little a because both blocks have the same acceleration value there. They're both moving in the same direction. We'll do a Newton's second law equation for B as well. We're saying there's no vertical component, so we only have one force to be the sum of the forces. That is the force of A acting on B. That is a positive force because it's pushing B to the right. And that's mass of B times the acceleration. The acceleration is also to the right, so that's a positive value there. In this case, we know that the mass of B is 5 kilograms. We know that the acceleration of A and B is both 9 meters per second squared. This allows us to say that the force of A pushing on B would have to be 5 times 9, or 45 newtons would be the force of A on B, and then that would also be the force of B acting on A. In either case, this is a magnitude. We haven't drawn the little line on top, so we're looking at how much they're pushing, and they're pushing off 45 newtons against each other. If we know the magnitude of the force of B pushing on A is 45 newtons, this is the magnitude right here. We dealt with the direction with the negative sign. Then we can say the force of the hand minus that 45 newtons that is acting of, that's B pushing back on A, is accelerating our block A, with a mass of 1 kilogram, with an acceleration of 9 meters per second squared. And so if we get a 9 here plus the 45, we find that the force that the hand is pushing has to be 54 newtons. this 54 newtons makes sense. We can double check it. We know from that internal forces, this internal force of B pushing on A and A pushing on B, keeps the system together. It keeps the two blocks moving together, but it can't actually make the system move. Only external forces, forces that act outside or through the walls, so to speak, of our system, can cause the system to accelerate. So, for example, if the surface wasn't there, gravity is external to the system. Gravity could make the blocks fall downwards together. In this case, they're sitting on the surface, and so the normal force and gravity balance each other out. Then the only external, unbalanced external force is the force of the hand pushing on this system. If the whole system has a total mass of 9 meters per second, the total system has a total acceleration of 9 meters per second, a total mass of 6 kilograms, then the external force would have to be 6 kilograms times 9.9 meters per second squared, which would be that 54 newtons. It's another way of checking our work.